Newton's third law is a statement about forces, the nature of forces that we use every day. What it says is that all forces exist in pairs, and we refer to these pairs as action reaction pairs. And so, what it says is that for every action force, there is a reaction force, and this reaction force has the same magnitude as the action force, but it has the opposite direction. So it is anti-parallel. The two forces are anti-parallel. So a way we could just write this out symbolically, and we need to pay attention to what is acting on what. You know, is the floor acting on the box, etc. And so we have the force that object A exerts on object B. So this is the force of A on B is equal to the same magnitude but opposite direction of the force that B exerts on A. So this is how we can symbolically write out an action-reaction pair. One of these is the action, one of these is the reaction. It doesn't matter which is which. It's not like one causes the other. This is the way that all forces exist. So take for instance a picture of the swimmer here. The force of the wall on the feet and the force of the feet on the wall is an action-reaction pair. We see that we have these two forces. So the wall and the feet go to the left and the feet on the wall go to the right. And one way you can always note if it's an action-reaction pair is that these get flipped around. A on B, and then it becomes B on A, right? So these get flipped around here, and you have to have the same magnitude in opposite direction as well. The way we make use of this is that, well, she is trying to, we know that a force is a mass times acceleration, right? So the direction of the force will be the direction of the acceleration, and she is trying to accelerate to the left. But what she does is she exerts a force to the right. So without this action-reaction pair, this force she exerts to the right would never accelerate her to the left. She must be accelerated by the reaction force. Her action is the force her feet exert on the wall. Then there's a reaction at the same time that the wall exerts on her feet and accelerates her to the left. We can, if you think about how you walk, if you're you're pushing back, or if you want to go this direction, if you want to have an acceleration in that direction, then when you take a step, you push back with some force this way. And I should actually draw this. You push back with some force this direction, and the ground pushes back with equal force in opposite direction. So, and this is generally the way that your foot interacts with the ground is through friction. So then there is some frictional force the ground exerts back on you, pushing you forward. If you try to go out on ice and you try to walk forward, it's very difficult to do because the friction is less when you have ice. If you're wearing cleats, then you can get a much larger frictional force, and so you can apply a larger force this way, and the ground will apply a larger force off to the left there and accelerate you faster. Similarly, if you look back at our definition of weight here, we had the earth, right? And so we had the earth, and we had an object up here, and we said that the object's weight was the force that the earth exerts on the object, on the mass. Well, there's a reaction to this. Okay, so the reaction to the force of the earth on the mass, I must flip these around, so it must be the force of the mass on the earth, and it must be the opposite direction and equal magnitude. And so we said this was actually equal to mg, where this was m. And so the force that the mass, the force that the mass exerts on the Earth is the same magnitude, still equal to this mg, and it is upwards. So although the Earth pulls this ball downwards, the ball pulls the Earth upwards as well, and there's an action-reaction pair to this. It exists in contact forces as well as field forces. If you put two magnets together, it's not like only one magnet feels it. Both magnets feel the force. The reason that we don't necessarily observe the ball pulling the Earth upwards is that we have, force is mass times acceleration. So if I have a tiny little mass here, this could be a tiny mass and a big acceleration, or we could say this is a very large mass times a very small acceleration. And so we don't perceive the acceleration of the Earth because the mass is so large that we don't notice the acceleration of the Earth.